Yeah. So internal energy is used in the thermodynamics topic, and thermodynamics doesn't deal with the micro cases or quantum cases of the nuclear reactions. So for macro cases, it is defined as the energy stored within a system, or if you think for an object, within an object that is exclusively the object's own ownership. What I mean is that, let's say, you can have an object to have some GP because of the effect, because it exists in a gravitational field produced by another object. For example, because of the existence of Earth, any object that is higher than the surface of the Earth might have some GP with respect to the surface of the Earth. So GP is not a form of internal energy. Similarly, electrostatic potential energy. For example, if you place a charged particle within an electric field, it will experience a force depending on its charge type and the electric field strength of that field. So that is also produced from an external factor. That energy is not an internal energy of that charged body that we're placing. Internal energy has to be entirely exist within the object by its own virtue. So thermal energy, I know for a fact that thermal energy is part of internal energy. Elastic strain energy or strain energy simply, that can be also internal energy, but I'm not really sure about chemical energy. I'm a bit confused about that. I need to look up some literature for that. So here comes the definition which works for you, that satisfies your examiners. Internal energy, this is just another name of the thermal energy stored in the object. Internal energy is the sum of random kinetic energies of the particles due to their random motion, and potential energy of the particles due to their intermolecular forces. So together, these two type of energies summed up together gives us the internal energy. That's the theoretical definition. The total internal energy stored within a system is determined by values or parameters of the system currently, and it is independent of how the current state is arrived at. This last point is important for you to understand one thing. Let's say, if you think in terms of internal energy, let's say you have 1 kg of water, and let's say you want to measure the amount of heat energy stored within within the water at, let's say, 30 degrees Celsius. So you can arrive at this 30 degrees Celsius by heating up some cooler water to 30 degrees Celsius, or you could also reach to this level by cooling some warmer water down to 30 degrees Celsius. I mean, how you arrived at this 30 degrees Celsius point would not determine or would not affect how much energy would be available to exactly 1 kg of water at 30 degrees Celsius. So how the process path would not matter. So this is also another meaning that this phrase or this last sentence, irrespective of the path of or how the current state is arrived at, this also implies the whole idea that external fields or external processes outside the object or outside the system that you are considering right now, they are not going to attribute towards the addition or subtraction of the internal energy of an object. Next paragraph reads, average kinetic energy of the particles is proportional to temperature, and increased potential energy is stored when the particles achieve greater separation. So this is an important part, that kinetic energy of the particles is proportional to the temperature, and potential energy is relevant towards the intermolecular spacing. Bigger intermolecular spacing means more P is stored. One of the ways, yeah, I mean, you can essentially try to visualize is that, let's say an object is made up of 1000 molecules, and they are all clumped together. If you want to expand this object, you have to somehow work from an external source onto the molecules and separate out those molecules slightly away from each other. Now, the virtue of intermolecular energy would be that intermolecular force would be to bring them all back closer together. The virtue of intermolecular force would be to bring all the particles close together. So one of the important bit is that if we want to increase the separation of these particles, or average separation, that's also pretty important in many of the cases. The word average is a very commonly missed out word, which I'm gonna tell you in a bit. You'll see the implication of that thing. So if we want to increase the average separation of the particles, we have to somehow do some work against the intermolecular forces and spread them out. It's very much like if you want to extend a spring under tension, then you have to do some physical work from the outside, and that's only when you can extend the spring. So for you to achieve that, you essentially have to do some external work, and the amount of external work that you'll be doing on those molecules you will be storing that equal amount of energy within those molecules as potential energy, which happens due to their own intermolecular forces. You have to understand that intermolecular forces of an object or among the particles of its own is not dependent on any physical factor. That is an inherent force that exists within the object because of its own existence. So that's another idea. So we have some, it says that both of these factors can individually or simultaneously affect the internal energy of the system, of a system. So we're gonna see 3 different examples over here, which can give a bit of an idea for what we are trying to cover. Number one says during evaporation, state change occurs at the same temperature. So the water molecules which get evaporated has the same average kinetic energy as the water molecules which are remaining in the container. Now, this might be a bit difficult for you to accept, but once again, I would like to take your attention to this line. Average kinetic energy of the particles is proportional to temperature. Whenever evaporation is happening, for example, let's say you have some water at RTP for 20 degrees Celsius in open to atmosphere, you're having continuous evaporation and you are converting the surface, high energetic surface molecules into gaseous state or vapor state. Because all those gaseous molecules are also going to be at 25 degrees Celsius as the liquid is also at 25 degrees Celsius. And now, yeah, so we might as well say that the evaporation, when the evaporation is happening, the average kinetic energy of all the water molecules is exactly same as the average kinetic energy of all the gaseous molecules as well. Now, some of you might feel like that, so evaporation produces cooling. True, evaporation does produce cooling, but we are assuming here that for the sake of this discussion, that as long as the evaporation will happen, that temperature difference is going to be pretty small. But if the temperature difference is significant, then you might as well say this is not true. For what I mean is that evaporation is happening, so high energetic kinetic molecules, high kinetic energetic molecules are leaving from the water surface, that way which you have learned in our O levels, because in our A's thermal energy was altogether skipped, so it's now once again popping in your A2 level. So evaporation does produce cooling, so there the remaining liquid is going to be somewhat cooler compared to the air surrounding, as long as we allow the evaporation to keep on happening. That's true, but for the sake of this discussion, assume that the evaporation is not producing cooling. Assume that. So if the liquid temperature and the surrounding temperature are exactly same, then we can essentially say the kinetic energy available, average kinetic energy available, damn it. So yes, muted and airplane not on. Good. Sorry. So uh, so if you consider that both of the objects are kept at the same temperature, the average kinetic energy of both the states would be exactly the same, but there would be some variation. Sorry. But there will be some additional, I mean, the total energy available to the gaseous molecule will be definitely larger compared to the total energy available to the water molecules. If we read on, that this is because the temperature is same. However, in the gaseous state, the average potential energy of the water molecules is far greater than that of the water molecules of liquid state. In evaporation, intermolecular spacing got increased, and work had to be done or energy had to be provided to give them the increased separation, comma, working against the intermolecular forces. So because we had to separate them out, we had to do some physical work. So energy had to be provided to the particles which converted into gaseous state. So now they will have increased P, but not increased K, because temperatures are same. The only factor we're gonna cover for your syllabus that will affect the kinetic energy of the particles is gonna be temperature, and temperature only. And separation, molecular separation, is the other factor by which we can determine how much potential energy is available. Example 2, pressure cooker. The volume of the content remains same, so spacing cannot change. So think about this, that we have some gas locked up in a pressure cooker. As energy is supplied, it increases the average kinetic energy of the molecules and temperature. So to understand this thing, let's say within a pressure cooker, you have kept, let's say, 2 million air molecules, and you have put it onto the stove. Those 2 million air particles are residing within the same internal volume of the pressure cooker. Even when you start heating up, start providing heat, the pressure cooker is not gonna give up these air molecules. It actually does eventually whenever for the nozzle of the pressure cooker, it does the hiss thing. Assume that this is not happening for our discussion. So it's just a closed container where the air molecules are heated up. So because it will be the same number of molecules available within the same amount of internal volume of the pressure cooker container, so the average separation of those molecules would be pretty much same. But as we slowly keep on adding heat to the system, the temperature of the gas will rise. This will essentially lead up to the increase of the average kinetic energy of those particles. Because there is no possibility for separation increase, so the potential energy of those particles would not increase. But because the particles can move faster, that's why that their kinetic energy, average kinetic energy, will increase, which in turn will also increase the pressure of the container. Because pressure, if you remember from your O levels of stuff, that আচ্ছা আমাদের pressure volume আর pressure কথা হলো পরে আসতেছে. So let's have a look over here. For example number 3, or is it covered over here? কোনটা দিয়ে কি
স্যার একটা কোশ্চেন ছিল।
একটু ওয়েট করো, একটু হাত উঠাও, আমি দেখতেছি। Achha, I don't see it here. So I might as well help you remember about the pressure thing that I was trying to tell you, and that is that হ্যাঁ তোমাদের এটা কেমিস্ট্রিতেও আছে, ফিজিক্সেও অল্প একটু করে আছে। So pressure পার্টটা হচ্ছে এরকম যে for a fixed amount of gas that we are working with, for a fixed amount of gas. So now whenever I say this, I'm considering that pressure is already a constant. So for a fixed amount of gas, pressure of a certain gas is expressed by the phrase the rate of collision of the molecules themselves, among the molecules themselves and with the container wall. Rate of collision, this is the key phrase to represent pressure. Rate of collision, actually a rate of collision এর সাথে speed of collision টাও affect করে, কেন affect করে বলতেছি। Whenever you can essentially have bigger amount of pressure whenever each molecule will exert a bigger force onto the same amount of surface. So if let's say you have, for example, if you consider for the case of the pressure cooker, for example number 2, we have to cover over here. At lower temperature, the particles are going to move slowly, so they are going to take longer distance to cover the average intermolecular spacing and do the collision. So for the sake of easy understanding, assume the Brownian motion is definitely going to happen. The particles are going to have random distribution of kinetic energies, and their separation is also not going to be equal as well. But if you consider for an ideal uniform scenario, let's assume the particles are all separated out at equal distance from each other. So if you try to visualize that, to make one collision, one of these particles has to cover that intermolecular space and go ahead and hit the other particle. So some amount of time is required to make this journey possible. If the velocity of the gas molecules are small, then they are going to take a bit longer to cover that distance. So you'll be having fewer collisions per second. Compared to a scenario, if the temperature of the gas is higher, in which case the average velocity of the gas molecules are much higher, so they're gonna cover that in between space more faster. So and also they are gonna collide with each other with bigger amount of momentum, because now we are talking about bigger velocity, so their momentum will also significantly increase. So each single collision will exert bigger force, and there will be increased number of collisions per second. Both of these factors would increase the amount of force that the collisions will exert onto the inner wall of the container. Hence, we say the pressure will increase.
Sorry, can you explain the last part again?
Yes. Each of the collisions will exert bigger force because they'll be colliding with a much higher speed or a higher momentum. Higher velocity multiplied by the mass of each molecule gives you a higher momentum, and also each collision, and there will be bigger number of these collisions happening, or increased number of this, when a rate of collision would increase at a lower speed, a lower temperature. The number of collisions that the particles were making with themselves and with the container wall, that number is something. And at a higher temperature, that number of collisions happening per second, that will also increase. So you're going to have more force exerting collisions, and the number of those collisions are going to be even bigger. So that will essentially may increase the pressure. One of the easier example, which is similar to this idea but not essentially same, is you can compare what happens for the physical understanding of how air resistance works. If you come to think about it, you covered air resistance in your O levels and AS level for the theoretical part, but not for mathematical calculation. I mean, if you think about it, that the way air resistance works, if you have let's say you have a rectangular surface that you are trying to move across atmosphere. If you move the rectangular piece slowly, then you will be colliding with each air molecule with a lower speed, and by Newton's third law, to make its path through the atmosphere, the surface will hit the air molecules, and before the air molecules move out of the surface path, this molecule will also hit the surface in the opposite direction of the velocity, and then they're going to move away. So each of these air molecules are going to exert a small force in the opposite direction of velocity onto the surface, and that's basically how we create the air resistance. If the object moves slowly, then the force involved in each of these collisions will be smaller, and the number of collisions that the surface will do with the air molecules would also be smaller, compared to the case if this surface or if this object starts to move faster. Because when the object will start to move faster, each of the collision with the atmospheric particles would involve bigger amount of force, and also you will be colliding with bigger number of particles because you'll be simply covering much longer distance through the atmosphere. So you'll be covering a bigger number of molecules. So both of these factors, more force involving a collision from each collision, and bigger number of collisions than earlier, both of these together will essentially increase the air resistance. So pressure is also works something like that. The momentum of the collision is also involved, and rate of collision is also involved. তোমাদের সিলেবাসে মোস্ট ইম্পর্টেন্ট ফ্রেজ হিসেবে রেট অফ কলিশনটাকে হাইলাইট করা হয়েছে, বাট কিছু কিছু মার্ক স্কিমে দেখবা যে along with the idea of rate of collision, they have also included the phrase of individual energies being more energetic, or individual collisions being more energetic, or individual collisions being providing bigger amount of force compared to earlier. So in some of the mark schemes they have attributed both of these factors, but if you are going for one factor only, the preferable phrase or the more important phrase as per your syllabus is the rate of collision or number of collisions per second. আচ্ছা শুভ্র, তোমার একটা কোশ্চেন ছিল, কোশ্চেনটা বলো।
স্যার আমি বলতে চাচ্ছিলাম কি, স্যার আসলে এভারেজ কাইনেটিক এনার্জি বাড়ছে যখন আমরা যে প্রেসার কুকারে রাখতেছি, তাই না?
ইয়েস,
মানে যখন আসলে আমরা প্রেসার কোনো একটা সিস্টেমে রাখতেছি না, যখন কোনো কন্টেইনার নাই বা উপরে কোনো লিড দেওয়া নেই, তখন কি তাহলে স্যার মানে এভারেজ কাইনেটিক এনার্জিটা সেমই থাকতেছে সবসময়, বিকজ কনস্ট্যান্টলি ইভাপোরেট করে চলে যাচ্ছে না?
তুমি কি एग्जांपल 1 এবং 2 কে মিক্স আপ করতেছো, ইভাপোরেশন এন্ড প্রেসার কুকারকে মিক্স আপ করতেছো?
আই এম নট শিওর, আমি ওই ফার্স্ট পার্টটা আসলে ঠিকমতো একটু বুঝি নাই মনে হয়, একটু কনফিউশন আছে।
বলো কনফিউশনটা কোথায়, which part is apparently. Try to understand these setups individually first, and then you can think about the mix up. The mix up of these two things actually happen for a large scale of what we call weather happening. পুরো ওয়েদারের মধ্যে তো কোথাও কোনো ঢাকনা নাই, বাট ওয়েদার যখন হয়, ফর এক্সাম্পল তোমার কোনো জায়গাতে সাইক্লোন হচ্ছে, কোনো জায়গাতে লো প্রেসার ডিপ্রেশন হচ্ছে, কোনো জায়গাতে হাই প্রেসার রিজন ক্রিয়েট হচ্ছে, how does that happen? That I mean, these two things can happen without a physical boundary. That's possible, but I'm not essentially getting into that at the time being. তোমার কোশ্চেনটা কি আসলে, try to think about your question.
স্যার ফার্স্ট পার্টটা আরেকবার একটু বুঝান তো, তাইলে আই গেস ক্লিয়ার হবে।
না, ফার্স্ট পার্টটা একবার বুঝাবো না। If you have any question, you can ask me, or you can look at the algorithm. This is very simple word. The idea is very simple. As long as the temperature of the liquid and the gas is same, you will have the same average kinetic energy of those particles, individual particles. But if your separation is higher, their P is going to be individual P, or per head, per molecule P would be bigger. To separate,
যদি সেপারেশনটা বেশি হয় তাহলে পার হেড পি বেশি হবে, তাই তো?
yes.
আচ্ছা বুঝতে পারছেন ব্যাপারটা, মানে লাইক স্যার তাহলে ইভাপোরেটেড যখন হয়ে যাচ্ছে তখন তো বেসিক্যালি কেইটা কমে যাচ্ছে আমাদের পি এর কারণে, ইজন্ট ইট?
No, it isn't.
পি বাড়লে স্যার কেই কমবে না, ইজন্ট ইট লাইক দ্যাট?
I never said that the total energy of the system has to be constant. We can provide energy from the outside.
But as long as the spacing is less between the molecules, K will be higher, right?
No, as long as the K is affected by temperature. Read at this paragraph. Average K of the particles is proportional to temperature. So average K of the particles will be controlled by the factor that is temperature exclusively, and spacing will affect the potential energy. Now you might wonder that, well, if the P has to increase, this energy has to come from somewhere. You might be wondering about that. There is a reason for this. Whenever evaporation is happening for an open water container or open liquid container, the particles of the liquid are gonna evaporate out, so they are gonna have their P increase. This energy has to come from somewhere. One of the ways you can take this, that this energy will come from the huge amount of heat energy available to the open atmosphere around, and the ground and the container body and everything. Because I mean, if you consider for our example, we can pretty much consider the atmosphere and surrounding atmosphere plus ground sort of like a elliptical ground for charge. I mean, you can take small bit of energy out of it, but the temperature of the atmosphere would remain the same.
So basically potential energy টা এইভাবে বাড়তেছে স্যার, রাইট?
Yes, as the evaporation happens, the potential energy increases. Okay, Abiyaz.
Sir, I have two small questions. Like, for the pressure cooker one,
Yes,
in a fixed volume, what would the graph of a average separation against temperature graph look like? Would it look
it should be a horizontal flat line.
like completely?
Yes, because you are not allowing the gas molecules to escape out of the container. So even at lower temperature, you have same number of gas molecules occupying same amount of volume. Even at a higher temperature, you have the same number of gas molecules occupying the same amount of volume. They're gonna move faster, but they are gonna be that their density per volume or number of molecules per volume would be exactly same, because you're not introducing more gas into the system. You're not allowing the gas to escape out. So per volume available per molecule would be exactly equal. Total internal volume of the pressure cooker divided by the total number of gas molecules, that quantity would not change.
So average separation is just a substitute for like volume.
Volume is also a factor, and also the number of particles is also a factor. If you want to, average separation comes from total volume available divided by total particles involved. So if you change any of those, you can have the average separation varied.
So if both are fixed, it will just be a horizontal line.
Yeah, non-zero horizontal line, by the way.
Yeah, yes.
And
Nice.
another one.
The second question, sir, is the total internal surface area related to gaseous pressure. For example, the 3D shape with the least internal surface area is a sphere, compared to a more folded container. If we increase temperature of the gas in both containers, will the internal pressure differ from these two containers?
Are they connected?
No, they're not. Like, they're separate, but they hold the same amount of volume of gas, except one, they're like two different natures. One is a greater internal surface area, one is less internal surface area. So will the pressure increase in the both of them be different?
At the same temperature?
Like, we're increasing the temperature by the same amount of the same volume of gas. But the only thing that is different is just the internal surface area of the container.
For an ideal gas, the pressure would increase by the same amount. We're going to see about that mathematical derivation after a while, so I can convince you of those facts in a bit. This will be covered eventually.
Sir,
Relating that to the P by FA definition of pressure.
Yes. We will see about that in a bit. I mean,
Okay, sir.
We're going to follow through in that. Ashvia.
Sir, my question is, during evaporation, the higher energetic molecules leave the surface of a liquid. So can you explain it in terms of collision theory?
What is collision theory?
I mean, you said that particles collide and they exert a force. So during evaporation, how is collision related, or is it related?
Yeah, collision is definitely related because particles are never actually absolutely free from each other, honestly speaking. So if you consider for the scenario for an evaporation, we are trying to compare one, I mean, this example over here. I'm going to address your question, but let me just specify what this example mean for the words that are over here. Uh, this example is trying to compare one single water molecule as it evaporates from its liquid state into its gaseous state. That's what this example is trying to cover. So if you measure the potential energy, average potential energy of one of the water molecule at its liquid state, it would be somewhat smaller, or significantly smaller, it's not somewhat, compared to if you measure the potential energy of that same water molecule once it has evaporated. However, in both of the states, because the kinetic energy available to these particles would be exactly equal. And now, if you think for the idea of collision, the particles will definitely collide with each other. Even at liquid state, the particles are not essentially joined with each other like a three-dimensional fixed spacing like solids. So the particles will essentially collide with each other as clusters, and also in the gaseous state, the particles will be completely free of each other, but they are also going to have Brownian motion, so they're going to collide with each other as well. And because of this collision, the energy will be dispersed out. But what we are trying to get, I mean, if you think for the if you try to extrapolate the idea of the collision into the sense of pressure, we are allowing the evaporation to happen to an to open atmosphere, not on a closed container. So the number of molecules available in the atmosphere because of the evaporation process will increase, but that increase would be a very small percentage, I mean negligible percentage of the total number of molecule available in the atmosphere. So because it's an open atmosphere that we are considering, the pressure of the atmosphere would not actually change significantly. I mean, theoretically, you can calculate this out to have a very small value. I mean, you might have uh, a lot of zeros after the decimal point, then some digits are going to show up. What I'm trying to mean is that when the evaporation will work, we'll be adding more water molecules into the atmosphere. So if you consider the whole atmosphere was, I mean, was stationary, or there was no other change happening to the atmosphere other than our evaporation process, then the total number of molecule available in the atmosphere does actually undergo an addition value. It actually increases. But because the atmosphere has a pretty large space to work with, it's not going to practically experience any pressure variation. I'm not sure if I answered your question, but that's what I can make out of it.
Okay, sir, you said that in the Brownian motion, energy gets dispersed. So which energy is it? Is it potential energy?
For the evaporation case, yes, but for the pressure cooker case, it will be kinetic energy entirely. I can help you understand a little bit more. Try to think of a water molecule that is at a water state and that is about to be evaporated. Now, this water molecule to become evaporated, it would require a fixed minimum amount of energy to convert itself from liquid state into gaseous state. How will this water molecule get this energy from? Is it going to come into the water as radiation, or is it going to be some sort of collision of the other particles simultaneously onto itself, which is going to give that kinetic energy at a certain instant of time? How would this water molecule achieve this amount of energy? Think in a physical process. So you have in the liquid, the particles are moving around, and the open surface of the water is exposed to the atmosphere. So atmospheric particles are continuously bombarding onto the water surface, and the water molecule particles are also having a bit of movement. Whenever we say that the high kinetic energy molecules evaporate out of the water surface, it is usually defined or described in a way that the particles are making random movements. So it is possible that one of those, there can be instances where multiple particles of air and also the whole water body might actually collide one single water molecule within a very short duration of time. like microsecond duration time or picosecond duration time. So all of those collisions energy will be actually transferred to this water molecule, which prepares it to become evaporated. So essentially that energy transfer happens by means of the collision of the particles. Does it make sense somehow?
Yes, sir. Thank you.
No problem. Shubho, তোমার কোশ্চেন পরে নিচ্ছে আবার কারেন্টলি ডিসকাশন করে নেই, I'll get back to you. Let's have a look at example number 3. Whenever some water is heated to boil, during the boiling process, the temperature does not change, but we need to provide heat energy continuous to maintain boiling. This applied or absorbed heat energy goes into two places. Have a look. Part of the heat energy is used to overcome the intermolecular attraction forces of the water molecules and to make them free of each other, which is basically the gaseous state. So you are going to spend some energy to strip apart the molecules, liquid molecules from each other to overcome the intermolecular force altogether. And then to occupy the volume for itself, the steam molecules have to push the atmosphere particles and do some physical work in the process. Part of the energy goes up to do this work. Now let me explain. You should be able to understand the first bullet pretty well, because that was discussed for this discussion quite a lot of time. Let me explain the second bullet. Try to think about it. Let's say you are applying heat to a certain amount of gas and a certain amount of liquid, and you are boiling the liquid. Whenever boiling will happen, this water molecules. I'm I'm using the term water in replacement of liquid in many cases, but I'm using them. I'm using them replaceably or alternately. So if you're heating up some water to boil it at 100 degrees Celsius, it's going to start to boil. So whenever a certain amount of water molecule, a certain amount of water has converted into gas, it's definitely going to occupy a much bigger volume. Think about it. Before the water came to boil, the space above the water was occupied by atmospheric molecules. The moment some water particles are converted into gas and the water is actually boiling, those vapor molecules will have to occupy their space in the atmosphere. To make that happen, it has to push out the atmospheric particles out of its path and make their own space in the atmosphere, which means the atmospheric particles have to be pushed outwards to make the space available for the water molecules themselves. So these water molecules will also do some work in the process of pushing out the atmosphere to make their own existent volume so that they can exist within the atmosphere. This is also there. So in the process of moving the atmosphere away, the water molecules or the gas molecules or the vapor molecules will also do some work. The amount of energy required to do this work will also should be provided from the heat source of the cooking pot. So if I just give you some numerical example, let's say, just to give you a bit of an idea, let's say you have 100 water molecules which are currently at water state, let's say a drop of water, and let's say if you want to separate out all of those 100 water molecules completely from each other, like you convert the entire water drop into gaseous state, let's say you're going to require 1000 joule. And when these water molecules are going to go up and altogether convert into gas, they have to push out the atmospheric molecules to make their own volume. Let's say these 1000 molecules are going to require let's say 20 joule worth of energy to make this physical work onto the atmospheric particles, which used to be earlier in its own space now. So the total amount of energy that you have to provide to this water drop to convert into gaseous state is not only 100 joule. Only 100 joule will not suffice. You have to provide a total of 120 joule to convert all of these 1000 molecules, convert from liquid state into gaseous state, even at the same temperature. Because you have to increase the separation, you have to overcome the intermolecular force among the water molecules, and simultaneously the particles have to be provided with the required amount of energy so that they can push out the atmospheric particles and make their own volume. So that's the third example, so which works a bit detailed for the process of evaporation. These three examples are basically three examples, but there can be a lot of different other examples. These are the three type of examples that you'd be working mostly for your work question paper. The question papers have a lot of these things. So yeah, that's that.
Sir, what happens when we apply exactly 100 joules?
Then you cannot boil all the 1000 water molecules. You might be able to boil, let's say, 95 of them or maybe 90 of them, and the rest of the 10 molecules would remain as water state.
Thank you.
স্যার ক্যান আই আস্ক সামথিং?
Yes, হ্যাঁ বলো।
স্যার আমি মানে এখানে কি আসলে ওয়ার্ক ইন হচ্ছে আবার ওয়ার্ক আউটও হচ্ছে দুইটাই? Isn't it something like that? Because হিট এনার্জি অ্যাবজর্ব করতেছে না স্যার মলিকিউল গুলা, আবার নিজে থেকেও তো ওয়ার্ক করতেছে।
So in this case, heat is being absorbed and work is being done.
মানে বেসিক্যালি হিটটা যে অ্যাবজর্ব করছে ওইটা দিয়ে ওরা ওয়ার্ক করতেছে তার মানে, তাই তো?
Yes, yes, heat is absorbed and work is done. আচ্ছা, আমি কি একটা জিনিস দেখতে এসেছিলাম, সেটা হচ্ছে
বাট স্যার ওভারকামিং ফোর্সেস আবার অকুপাইং ভলিউম দুইটার জন্যই কি হিট এনার্জি থেকে মানে ইউজ করতেছে?
yes,
আচ্ছা, so basically two times it has to does work.
yeah, the heat energy is absorbed has to go in two places. এটার কোনো ইয়া নাই।
No, sir, you have to find it manually.
Oh man. First law of thermodynamics গেল কই?
Sir, what are you exactly looking for?
I'm looking for the first law of thermodynamics. What expression do your syllabus have, or did they change the expression? First law of thermodynamics can be expressed in two different way. I'm trying to find out the exact way that your syllabus opines you to learn. I should find F, Control F. Yes, yes. So yeah, my notes are not futile. They are in line with your syllabus volume. Okay. So the next topic that we have is what we call first law of thermodynamics. I'm not essentially following once again the exact sequence that your syllabus is designed for. I'm following my personal preferable sequence because I like to teach the chapter in this manner. And one of the key things that I'd like to remind you that all the stuffs that you have learned in your O levels regarding thermometers and heat capacity and latent heat, they are gonna show up once again. I'm gonna help you remember them. I'm gonna have a revision on those topics as well, but you will have to remember them. So all of those old stuffs are not given over here, but they are just gonna pop up over here, basic O-level stuff. So I'll cover this parts a little bit as well. So let's have a look at the first law of thermodynamics. This law helps us to accurately calculate multiple energy values of a system. The first law of thermodynamics reads like this: delta U equals to Q plus W. It is really important that you understand the description of these three variables exclusively. Delta U means increase in internal energy for this expression. Q means heat supplied to the system. W means work done on the system. In this expression, we have written that delta U equals to Q plus W. What we're trying to mean is that to increase the internal energy of a system, we can achieve it in two alternate ways or simultaneous ways. You can apply heat energy into the system, which is going to increase its internal energy, because like I said earlier, that providing heat energy would can increase its temperature. So that can add to the internal energy of the system. Or you can physically do some work on the system. For example, you can squash down a certain amount of gas which is locked down in a cylinder attached to the piston, or you can squeeze a certain amount of elastic material to give it some elastic potential energy. So whenever you will do physical work on a system, the amount of work that you are doing on the system will also be stored within the system as energy. So you can increase the internal energy of a certain system by doing two type of energy input. In this case, both Q and W means energy input. Have a look at the prepositions. Q is referred to as heat and heat supplied to the system. So heat is going into the system, and W is defined as work done on the system. Work is being done on the system means that work is being added to the system. So your external source is working on the system. So in this case, if the what is really important for this thing to understand, if we read further, have a look. For a given gas at a fixed pressure, delta W equals to P into delta V. This is a formula that we have seen in our. Did you see this formula in our O levels?
Yes, sir.
V1 equals to P2 V2.
Delta V, sir.
Nah.
Yeah, we came across this in AS. Some questions.
Acha, sorry, you didn't see this in your O levels. You came across this in your AS to calculate the amount of work done on a certain amount of gas. It only this formula was introduced. Okay, so we can calculate. So this formula has a limitation, by the way. Have a look. For a given gas at a fixed pressure, the work done is given by P into delta V. So because we are not going to be working with integration for your A2 syllabus, I mean your physics syllabus altogether, so we are not introducing where both of them can be a variable. I mean, if you think practically speaking, let's say if you start to apply heat to a system of gas, I mean, logically speaking, both of your pressure and volume could also change simultaneously. But if that is the case, then you are gonna have to deal with a curved situation where calculating the total energy supplied might require some sort of integration or square counting. For whatever reason, the CA people decided not to include that. So they're gonna only give you mathematical problem where your work done has to be calculated for a fixed pressure volume changing scenario. So what I mean is that for a given
Sir,
gas, একটু শেষ করি question
স্যার
হাত
একটু
ধরে রাখো।
লাস্ট পার্টটা একটু আবার বুঝাবেন, আমার কানেকশন চলে গেছিল, শুনতে পারি নাই।
আচ্ছা আমি শেষ করি, তারপর তোমার লাস্ট পার্টের কোশ্চেন আবার নিচ্ছি, একটু ওয়েট
আচ্ছা
করো। So for given gas at a fixed pressure, delta W equals to P into delta V. So this is very important for you to understand that this delta W, what would be the sign of this delta W whenever we'll use that value into our equation. I mean, the signs would be very important because it is very, you have to understand that all the quantities that we have mentioned in the first law of thermodynamics, internal energy, heat energy, and work done, they're all scalar quantity. But whether this is producing some positive variation in the system or is it producing some negative variation in the system, depending on that, you have to put their sign into your equation logically. If your system, if you extract out some system out of if you take out some heat from your system, in that case Q for this equation should be negative. If you extract out some heat from your system, because in this the equation, have a look, Q was defined as what? Heat supplied to the system. So if for Q to have a positive value, heat has to be entered out from outside into the system. If heat leaves from the system, then Q should be negative in your equation. Similarly, if external work is done on the system, in that case W should be positive, which is comes over here, that compression means work is going in, W positive. Because think about it, if you're doing compression, then you have to actually squeeze the object from the outside, so your W would become positive. Expansion means work is going out, so that would mean work would be negative. So you have to understand what is actually being done. Expansion essentially would mean what? Expansion is simple example ছিল হচ্ছে the second bullet of the third point that's just above, that to occupy volume for its own, I'm reading here once again, to occupy volume for itself, the stream molecules have to push out atmospheric particles and do some physical work in the process. Part of the energy goes out to this work. So in this case, the system of the gas or water molecules, they were actually pushing out the atmospheric particles to make their own volume available. which means they were actually doing some work on the atmosphere. So work was going out of the system. But in this case, the W was defined as work done on the system. So for this part of the statement, the system was doing work on the atmosphere, not the other way around. Atmosphere was not doing work on the system. So if you have to work with that example for your first law of thermodynamics, in that case, W should be placed as a negative value. We're going to see more about this plus and minus questions after a while as we slowly go on forward in our lecture. And also increasing internal energy or delta U is referred to as increasing internal energy. So if by any physical process the internal energy of the system gets increased, then delta W should be positive, and if the internal energy reduces, then the delta W should be negative. So it's important that you understand the prepositions of this question very, very well. Delta W means, once again for the last time, increase in internal energy. Q means heat supplied to the system. W means work done on the system. I'll be going further in a bit in the discussion. So তোমরা যারা হাত উঠেছো question মাথায় রাখো, আমি question একটু পড়ে নিচ্ছি. Just give me some time. Because the part next, I mean, you might as well have all of your answers as when I'll finish. So wait for me to finish. Hold your horses. So this is a basic expression for the first law of thermodynamics. However, if you turn up internet and if you look up for first law of thermodynamics, in many other cases, you might also come across the idea of first law of thermodynamics, which might as well look a bit different. So I'm gonna write a different equation and start to make sense with you of the different equation. That this different equation that I'm about to discuss right now is not essential for you to understand for your syllabus volume, but I'm still going to discuss it anyway, so that anytime you come across this different version of first law of thermodynamics, you're not stumbled, you're not startled, so that you know that yes, I understand what this means as well. Because you should be prepared to take on whatever physics you have, because ideally speaking, physics of a certain thing would not change depending on how we want to describe that scenario. That's not gonna that doesn't happen.
স্যার একটা কোশ্চেন ছিল যে
হ্যাঁ, কোশ্চেন একটু পরে করো. Hold remember your questions. কোশ্চেন আমি একটু পরে নিচ্ছি. So yeah, I am starting to use my writing pad. I hope I'll be good at it. So the first thing that I would like to write that another in this case our equation was like this: delta W. Why am I not writing?
Sir, you selected the selection tool, not the pen.
Oh. Thank you. I like this pen better. This pen is nice. And this one also.
The first one was better, I think.
Okay. Anyway, we'll do either. So the equation that we just came across looks like this: that we had delta U equals to Q plus W. This was the equation that we have just come across, and this is the equation that your syllabus volume is going to work with. Another variation of this same first law of thermodynamics can also look like this: Q equals to delta U plus W. Now, this can also be an expression for thermodynamics, but in this expression, these variables will be described differently. Let me just tell you what I mean. So yes, what I mean is that if we have this expression, Q would be referred to as heat supplied into the system. So okay, I'm just going to write here. This would be heat supplied into the system, and the idea is that whenever we'll supply some heat into the system, part of that heat would be used to increase the internal energy. So this is increase in internal energy. And part of that supplied heat would be used to do work by the system. So this is defined as work done by the system.
Sir, by the system or on the system?
In this case, it means by the system. I'm going to write these things as well. This one meant the same thing as earlier. Left, right means the same. Q also means the same, but the only difference is that this W, for what is given in your syllabus version, This was to be read as work done on the system. Now, to make sense, why is it difficult on the system? Good. To make sense of this two equation, I'm gonna do some changes over here, and you'll see that it will just fall. It will become pretty easy. If I just take this W on the other side, what is gonna happen? Can I write this equation in this format? Delta U minus W equals to Q.
Yes, sir.
Here, the W meant work done on the system. That's why it was a minus sign. If I convert this minus into plus, I can simply write this W would become the work done by the system. And that basically is this formula.
Sir, work done on the system to more positive ধরছি, right?
Work done on the system টাকে আমরা এই ইকুয়েশনের জন্য পজিটিভ ধরছি, আর work done by the system কে আমরা এই ইকুয়েশনের জন্য পজিটিভ ধরছি. But these two things are not defined the same way. That's the difference that I'm trying to get in your head. This is reading as work done on the system. This one is reading work done by the system, which means this work done for this equation is the work that is getting into the system. This W over here for this expression is the amount of work that is getting out of the system. But inherently, they pretty much mean the same thing. Because if you just change the side, you get delta W minus W. So whenever this was minus W, this was still work done on the system. But if you want to express the same thing as plus, this will simply become work done by the system. So you can also write this expression like delta U plus W equals to Q. In that case, you can describe this W as work done by the system, because you just converted the minus sign into plus by changing the direction. So on the system work became by the system work. So you have reversed the direction of work done. That's why minus could be replaced with plus, which basically gives us the other expression of the first law of thermodynamics. So in some of the literatures in internet, other books, you might come across this expression, and that might be available. But you have to understand by looking at this equation that depending on the equation you have, you should know that which one means which part of the whole thing. So easier way to remember is this, that if you are trying to increase the internal energy, you can increase it in both two ways. You can either increase it by applying heat, or you can also increase it by increasing the actual by doing actual work. So you can feed the system heat energy. You can also feed the system work, which is also another form of energy. So in this case, this Q and W, they both have to enter into the system to make an increase of the delta U. That's one thing easier to remember for this equation. But if you look over here, the idea of this equation is that if you provide some heat into the system, part of that heat energy will be used up to increase the internal energy content of the system, and the system would be able to do work using a portion of that heat energy supplied as the work done on the system. So a fraction of this heat energy will be used up to increase the internal energy content, and another part would be used to do some physical work that will be going out of the system. So all the heat energy that you are supplying will not be used up for delta U. Some of the heat energy will be also used up to do some physical work on the external system. So that's the basic variation of these two expressions of laws that we have. Okay.
স্যার আপনি কি সেকেন্ড মানে লাস্টে যেটা বললেন সেটা ওয়ার্ক ডান বাই দ্য সিস্টেমের জন্য?
হ্যাঁ,
তাই না?
হ্যাঁ।
আর স্যার আমি বলছি যে ওয়ার্ক ডান অন দ্য সিস্টেম যখন, তখন তো অ্যাটমসফিয়ার কাজ করতেছে।
Yes.
দেন ওয়ার্ক ডান বাই দ্য সিস্টেম যখন, তখন কি উল্টা স্যার, অ্যাটমসফিয়ারের উপর কাজ হইতেছে বেসিক্যালি?
Yes.
আচ্ছা
Abias, bolo.
Sir, my questions were from a little back. It was about separation, sir.
Bolo.
When the separation of these gas molecules, when they're at their minimum, is potential energy zero?
No, potential energy is not zero. Minimum would mean potential energy is less at that point. Potential energy will be zero only at the position when the particles have no attraction of force onto each other, which is theoretically possible at infinite distance of separation. Practically, it is available for a specific value.
Sir, doesn't greater separation mean greater potential energy?
Exactly. But if you want to express it in terms of the forces, the force only becomes zero when their separation is infinitely big. As if bring the particles closer, their force doesn't reduce.
Okay, sir. So you're explaining using gravitation.
Somewhat like that, but I'll show you something else. This is how intermolecular forces work. This is the separation. This is the intermolecular energy. For a specific value of a separation, this is what we call the equilibrium state for a certain temperature. So beyond this point, up to this much, you would have the particles to be at equilibrium. If you start to increase up the separation, then the attraction force is going to slowly start keep on increasing up to this point. Beyond a certain point, the attraction force will start to diminish, but it will never become absolutely zero. You can see that this graph is becoming asymptote, but not touching the x-axis. So the farther you will separate them out, the force attracting them, if you think of all the forces are gone, even but still gravitational forces are still gonna be there. So hypothetically speaking, even if you get rid of van der Waals attraction force, electrostatic attraction force, and everything, you cannot simply get over gravitational attraction force. The only location where the intermolecular forces can be perfectly zero is at infinite distance. Whereas if you start to compress the object, for example, if you start to squeeze the object from this position, in that case, the intermolecular force becomes repulsive. So this negative force represents attractive force. This positive force represents repulsive force, which we slightly discussed in the idea of chapter of gravitation, but not quite because this was an idea generated from the Coulomb's law. So whenever we start to squeeze the object or reduce the intermolecular force beyond the equilibrium point, then the forces are going to be repulsive. So the object is going to try to revert or resist that deformation. So that's one another property that we have over here, which I think should make sense.
I understand, sir. At a certain point, the potential energy goes in one direction, and after a certain point, it goes in the opposite direction.
Yes.
And if the particles were theoretically set to merge onto a single point, then the potential energy would be infinite, right, sir?
Yes.
Okay.
Yes. If they could coalesce together so that their center of gravity would be actually in the same location, which is highly impossible. But in that case, their potential energy would have been infinite, not physically achievable. But,
sir,
but we can reach to this point, reach to this behavior whenever we talk about nuclear fusion.
Okay. And another
yeah, bolo.
In PV graphs, like pressure volume graphs, when they'll ask us to find the work using P delta V, it's always going to be horizontal lines in the area
Yes.
beneath them, right, sir?
Yes. We're going to see about that as well in the worksheets.
And the work, we can infer whether work is done on or by the system using the arrows on the graph, right, sir?
I do not prefer to rely on the arrow a lot because they can be a bit confusing at times. The way I prefer to teach the kids to avoid the confusion is that you try to make sense from the graph that are we squashing the gaseous system or are we expanding the gaseous system? If volume is expanding, then work is going out for this equation. Because we'll be using this equation for most of our working for your syllabus volume. But this can be available at other literatures or physics books as well. So we're not going to be working this one for using this one for our most part. We'll be using this one for our primary formula. So if the volume of the system gets increased, then or if the volume is expanding, then this should be negative. In that case, that would mean that the gaseous system is doing work on the external bodies and vice versa. So for the case of squashing, W would be positive. For the case of expanding, W would be negative. So other than direction of the arrow, it's easier to make sense of the plus and minus effect of the W sign if you try to physically try to understand that. Is it becoming, is it getting squashed or is it getting expanded? That usually leaves less room, much less room for confusion. That's what I mean.
I see, sir. Thank you.
Shuro, tomar aro question আছে? You still have your hand raised, so you can ask or drop the hand. যাদের question করা হয়ে
ড্রপ করে দেন
ঠিক আছে। So yeah, Arunima.
Sir, ওই যে ওই পার্টটা যে for a given gas at fixed temperature, fixed pressure, প্রেসারটা ফিক্সড কেন থাকে?
প্রেসারটা নেসেসারিলি ফিক্স থাকবে না, প্রেসারটা ভ্যারি করতেও পারে, বাট প্রেসারটা যদি ভ্যারি করে, আমরা যদি প্রেসার এবং ভলিউম দুটাকে ভ্যারি করতে যাই, সেক্ষেত্রে আমাদের পিভি গ্রাফটা হবে একটা কার্ভ। কার্ভের এরিয়া আন্ডার গ্রাফ বের করার জন্য তোমাদেরকে এসেনশিয়ালি স্কয়ার কাউন্টিং করা ছাড়াও তোমাদের ফিজিক্সে এ লেভেল সিলেবাসে আর অন্য কোনো মেথড দেওয়া নাই। তোমরা ফিজিক্সের এ লেভেলসে সিলেবাসে কোনো ইন্টিগ্রেশন করবা না, ইন্টিগ্রেশন তোমাদের ইনক্লুডই করা নাই অলটুগেদার। সো ওই প্রবলেমটা অ্যাভয়েড করার জন্য হোয়াট আই বিলিভ তারা ওই কমপ্লিকেসিটা দেয় নাই। বাট প্রেসার যে ফিক্স থাকতে হবে ব্যাপারটা এরকম না। বাট প্রেসার যে সকল কেসে ফিক্স থাকবে ওই সকল কেসগুলোকে নিয়ে তোমাকে ম্যাথমেটিক্যাল ক্যালকুলেশন করতে বলবে। আর যে সকল কেসগুলোতে প্রেসার ভ্যারি করতে পারে ওই কেসগুলোকে নিয়ে ম্যাথমেটিক্যাল ক্যালকুলেশন করতে বলবে না। দিস উইল নট বি পার্ট অফ ইউর ম্যাথমেটিক্যাল চ্যালেঞ্জেস। Physical cases pressure vary করতে পারে, but those calculations are not going to be asked to you to achieve. So I'm trying to put a line between what is possible and what is not possible, and what you are gonna have to do and what you're not gonna have to do. They're not the same thing. বুঝতে পারছি?
হ্যাঁ বুঝছি।
Pardon.
Sir,
Yes.
sir, সব আপনি যে বলেন স্যার ওয়ার্ক ডান তো স্যার স্কেলার কোয়ান্টিটি, সো লাইক আমরা পজিটিভ বা নেগেটিভ কেন ধরছি?
Because of the direction, because how that work done, we are trying to find out how does that work done or work done. Work done. Okay, work done. Work. How does that work done affect the value? We are trying
Sir,
to
sorry?
we are trying
Sir?
to figure out how does that work done affect the internal energy of the system. If work goes out of the system, then the internal energy will become less. If work gets then the internal energy of the system will increase.
Okay. Sir, আমার আরেকটা কোয়েশ্চেন ছিল স্যার, আপনি যে আরেকটা ইকুয়েশন দেখালেন স্যার।
Yes, second equation যেটা দেখালাম।
Yeah, second equation দেখালেন। Can you like go to that? Yeah. Sir, second equation-এ তো আপনি এখানে আমরা W টা ধরতেছি work done by the system, right?
Yes.
So আমরা যখন এটা লেফট সাইডে নেই, so work done into the system হয়ে যায়, কারণ নেগেটিভ হয়ে যায় W টা, right? So if we increase work done on the system now, so আমার তো decrease into internal energy হবে, increase হবে না স্যার, কারণ ভ্যালুটা তো ছোট হয়ে যাবে, right? কারণ Q minus W স্যার ভ্যালুটা তো ডিক্রিজ করতেছে, right?
For which equation? This one?
Sir, second equation টা, sorry. হ্যাঁ স্যার।
আচ্ছা আমি লিখি, if I just write this down, এটা হচ্ছে if I write this, so Q minus W equals to delta U. In this case, W was referred to as the amount of work done by the system. So one of the mathematical expression or value-wise expression that can make sense. If you supply, let's say 100 joule to a gaseous system, and it does 20 joule of work on the atmosphere, then the increase of the internal energy would be 80 joule.
Yes, sir.
Whereas over here, I can give another example. If you provide 80 joule of energy to a heat energy to a gaseous system, and also squash it to provide another 20 joule of work done onto the system, the total amount of internal energy change would be the sum of these two, which would be 100 joule.
Yeah, that's what I'm saying. So internal energy decrease করবে না একটা জায়গায়, আরেকটাতে increase করতেছে তো।
Internal energy দুই জায়গাতে increase করতেছে। এখানে যতটুকু হিট দিচ্ছি, এখানে the amount of heat that we're supplying here, all the heat is not increasing the internal energy, but that was the case over here. Here Q was added to W in the sense that all the heat that we're providing is getting added to the internal energy. All the work that we're doing on the system is also getting added to the internal energy. So total internal energy increase was bigger than the heat supplied, because with W, along with the heat supply, you're also doing some physical work on the system. You're doing both of them simultaneously. So you're inputting energy in both ways. That is the idea of this expression. Whereas this expression means that the amount of heat energy that you will supply into the system, all of that heat energy will not be used to increase the internal energy. Part of the heat would be wasted out.
So sir, আমরা একটা ইকুয়েশনে হিট এনার্জি কি লাইক বেশি দিচ্ছি, লাইক হিট বেশি দিচ্ছি, আরেকটাতে হিট কম দিচ্ছি।
Yes, you can put it that way.
We can put that way.
Yes.
Oh, awesome. Thank you, sir.
No problem. So if we move forward from this point, we are having at the next point we have the basic O-level stuff. First of all, we have the definitive equation for the degree Celsius scale, the relationship between degree Celsius scale and the thermodynamic scale, which is the Kelvin temperature. So you know these two equations, and then we have two equations over here. Capital C represents thermal capacity or heat capacity, which is the amount of heat required to increase the temperature, change the temperature of an object by 1 Kelvin, which has a unit of joule per Kelvin or joule per degree Celsius. It can also happen in that unit. But this is applicable for a whole object, not applicable for the material of the object because mass was not involved. This is heat capacity. Whereas if you go for small c represents specific heat capacity or specific thermal capacity, which is given by Q divided by m delta theta, which expresses amount of heat energy required to change unit temperature of the object for unit mass. So this one has a unit of joule per kg per Kelvin, or it can be also joule per kg per degree Celsius. This is a property of the material of the substance, which means that if you have multiple objects made from copper, depending on their masses, they can have different thermal capacities. But as long as they are all made from copper, they are all going to have the same specific heat capacity. Specific capacity can be considered to be similar of a property like density of a material or resistivity of a material. So that's that kind of the differentiating point that you can think in your head. And beyond this point, we have this expression. This is not supposed to be LF slash. I mean, this should be double slash. I would prefer a double slash over here because this might as well mean division, but this is not division. But what is being shown over here that latent heat of fusion or latent heat of vaporization, both of these things have the same numeric has the same expression in terms of variable Q by M. Q is the amount of heat required to make the state change, and the M is the amount of mass that we are trying to make the state change with for. So so this ratio of the amount of heat energy per mass is what we mean by latent heat of fusion or latent heat of vaporization, which is basically joule per kg. So one of the important bit for this equation to make sense is that because latent heat of vaporization or latent heat of fusion, these two variables are only going to be applicable to our mathematical calculation whenever the object is having its state change exclusively being stuck at a temperature of its state change. So let's say you are trying to melt some ice, so the temperature is gonna get stuck at the melting point till all the ice hasn't melted. So for that process, we're gonna use this expression. So latent heat process or state change processes are gonna happen when the temperature of the system is constant at the transition temperature, melting point or boiling point or condensation point or freezing point, however you consider for the duration of the state change. So that's why in this equation, we do not have degree Celsius or degree per Kelvin, because this is going to only happen at a fixed temperature. So simpler way to remember this, the use of these two equations, which I'm going to explain in the mathematical working even further, we're going to see, is that when temperature change will happen, this formula will come into action. This formula would essentially can be converted into Q equals to MC delta theta, which is the linear version if you just cross multiply it. So Q equals to MC delta theta is the to be used equation when there is a temperature change, but the state is same. And Q equals to MLF or Q equals to MLV, the product can be used for the case of state changes, or when the temperature is remaining constant, we are converting one object into another one. So depending using these two set of formula, we would have to do quite a bit of mathematical working, especially for the case of equilibriums and everything. I'm going to show you how to do this working. This mathematics are going to be slightly more complicated compared to your O-levels calculation, because this is your A2 level. But where this complication lies, I'll make it clear to you when those problems are going to pose themselves. For the time being, you just have to remember that these two formulas we used to use in our O-level syllabus. Currently in our A2, we are going to also have to start to use them once again. Okay, then we have gas laws. But before I get into gas laws, I'm going to take some questions. Yes, Mahim.
স্যার আপনি যে স্যার আগে একটা স্যার বলছিলেন না স্যার যে দুটো ইকুয়েশন স্যার আপনার মানে এনার্জি লসের একটা আরেকটা স্যার এনার্জি লস ছাড়া স্যার ওইটা স্যার আমি বুঝতেছি না।
এইটা
জি স্যার।
এই দুটো ওয়ার্ডের ডিফারেন্স খেয়াল করো, একটা হচ্ছে অন দা সিস্টেম আর একটা হচ্ছে বাই দা সিস্টেম। হ্যাভ এ লুক এট these two prepositions. For this one, the energy work done is getting into the system and adding to the internal energy of the system.
Yes sir.
For this case, this is going out as a portion of the heat energy. The example that I gave over here, that you are supplying 100 joule of heat into the system, only 80 joule of that energy is absorbed as the internal energy, and 20 joule of energy is not entering into the system. It is being spent on the external atmosphere or to the external bodies which is leaving from the system. So if work is done by the system, it means that energy is going or work is going out.
ও ওকে স্যার স্যার বুঝছি স্যার
Okay.
So, sir, এখানে minus হয়ে গেলে shouldn't that be work done into the system? Like,
Yeah, exactly. That's what I did over
তাহলে
here.
আপনি আবার না, I'm talking about the right equation. আপনি যে 100 minus 20 করেছেন, like plus তো এখানে indicate করছে work done by the system. তাহলে W টা হবে না, I mean তাহলে নেগেটিভটা হবে না work done into the system.
Well, W is by definition is the work done by the system, which means that if you are about to use this expression for your mathematical calculation, then the energy that will be leaving from the system is supposed to have a positive value. And this minus is that default minus sign coming out from the equation. So let's say you have a gaseous system, you just put into 100 joule of heat energy into the system, and before the system comes to an equilibrium or workable state, it is losing 20 joule out of the system. By definition, for this equation, work done by the system or work leaving from the system would be the amount of energy that would be posed or value replaced in the equation as positive energy. That's why there is no individual minus sign in front of this one.
So it itself is a positive value.
Yeah, by definition, have a look. This W means work done by the system. So for this equation, the energy that is leaving out of the system, the work done that is leaving out of the system is the positive amount of W, which is not the case over here.
Yes, sir.
Which is not the case over here.
And sir, আরেকটা question ছিল, আপনি একটা গ্রাফ দেখিয়েছিলেন যে separation versus potential energy. ওখানে একটা পজিশন ছিল যেখানে হচ্ছে ইকুইলিব্রিয়াম বলতেছিলেন, like can you explain what exactly is the equilibrium এখানে?
Equilibrium means this is the current intermolecular separation at which the relative potential energy of the particles are considered to be zero. Zero means that particles are not at a state of tension, neither at a tension of compression at this value. So let's say you have a, let me give you an example. Let's say you have a piece of, let's say a metal piece. Let's say a certain metal piece has a melting point of, let's say 800 degrees Celsius. So if you keep it at room temperature, at the room temperature, all of these particles have a specific amount of intermolecular spacing, and they're comfortable with that spacing. At that spacing, if you don't bother that that metal piece or those metal atoms, they are going to maintain that intermolecular spacing forever. So they are not trying to split out from each other naturally, neither they are going to automatically squash into each other to pose a smaller volume. They are at equilibrium means they are neither at a state of tension nor at a state of compression. But if you start to do something else, maintaining the same temperature, let's say if you try to extrude out the metal, then the metal is going to try to oppose that behavior. That is the case for the right side. As you slowly start to increase the separation, which means extruding out, you are trying to increase the separation of the particles. In that case, they are going to try to attract themselves more strongly up to a certain point. Beyond that point, they are going to give up, but the attraction would not become entirely zero. So this giving up point is basically what we defined in our elasticity chapter as the yield point or the UTS point. Do you remember?
Yes, sir.
UTS point was the highest point of your separation. So up till this much separation, the particles are still going to try to maintain their collaboration. But beyond this point, they are going to start giving up in random places. And that's for the separation, increasing separation. As for the decreasing separation, if you try to squash an object, the particles are simply going to try to repel that object, and this graph is simply going to go upward. Because if you are trying to squash some material, they're going to repel and repel, and they're going to further repel, because you cannot simply make everything to come into a single point, because the whole idea of particle is a theoretical idea. You cannot squash the entire metal into a much smaller volume without experiencing this repulsive force. So for this part of the graph, this is
স্যার
attractive.
মানে আর এর ওই পয়েন্টটা থেকে যখন হচ্ছে আমরা বাড়াচ্ছি তখন আর হচ্ছে
একজন একজন করে আমি কোশ্চেন নিচ্ছি তো,
আচ্ছা আচ্ছা
ওয়েট করো। So for this part of the graph, we are representing increasing of separation, which means we are trying to expand the material. And for this part over here, we mean compression of the piece, which means we are trying to squash the material.
Yes, sir. Thank you.
বুঝা গেছে?
জি, sir.
শুভ্র বলো, go ahead.
স্যার বলছিলাম যে তার মানে স্যার একটা পার্টিকুলার ডিস্টেন্সের পরে হচ্ছে ওদের মধ্যে আর পটেনশিয়াল এনার্জি হচ্ছে ধরে রাখতে পারবে না বা সামথিং এরকম কোনো একটা ব্যাপার হচ্ছে,
না,
রাইট?
একটা সার্টেন
তাহলে পয়েন্ট অফ ইনফ্লেকশনটা স্যার আসতেছে কেন?
এটা আমি এক্স্যাক্টলি পড়াশোনা করি নাই, বাট আমি যতটুকু জানি অতটুকু তোমাদেরকে বললাম। মানে what is the significance of the point of inflection, because in this case you can see point of inflection is not located at the lowest point, it is located here.
Yeah,
So
why? That is the thing I'm thinking.
I'm not sure about this thing. I really don't know. I have to study further to get to this answer. But the part that I just explained, I know this for a fact, but I do not know about the idea of point of inflection. I didn't study this part.
স্যার মানে একটা পয়েন্টের পরে হচ্ছে আর মানে এনার্জি চেঞ্জ আর নরমালি হয় না, ইজ ইট সামথিং লাইক দ্যাট?
No, beyond a certain distance, the strong intermolecular force start to really weaken up pretty fast. Up to from here to here, the intermolecular forces are gonna get even stronger with increased amount of force. This is sort of like the elastic behavior, that particles are still gonna get back to the origin state. So you have a very strong intermolecular force for a certain range, and then beyond a certain point of intermolecular spacing, the particles are not gonna get back to that original intermolecular force value naturally, because now they can have a much disturbance scenario. For disturbance scenario বলতে আমি যেটা mean করছি, for example, this is the E scale or the potential energy scale. Particles are always going to try to reach to their zero potential value. That's what I mean equilibrium. So whether you give them a negative potential energy or you're gonna give them a higher positive potential energy, the particles are naturally gonna try to reach to their zero potential energy. But beyond a certain keyboard separation value, this negative potential energy is gonna start to increase on its own. So even for increased separation, the particles are gonna get comfortable over here. So they are not gonna naturally go down here and reach up to the original shape. This is something similar to the idea of energetics in your chemistry classes. That if you have to make a reaction to happen, the reactant particles have to be somewhat energetic to reach to make the reaction, and then they're gonna fall down to a lower energy level. And by using some catalyst, you can lower that peak so that the reaction can happen more often.
স্যার নেগেটিভ পটেনশিয়াল এনার্জির ব্যাপারটাও বুঝলাম না, লাইক পটেনশিয়াল এনার্জি নেগেটিভ হয় কিভাবে?
In this case, they are trying to mean is that whenever we are separating out the particle, we are going to have negative potential energy. I mean, the absolute value of potential energy in this case is labeled as zero, not at infinite distance of the particles. It is labeled as zero when the particles are at equilibrium. So they have over here tried to represent the repulsive energy as positive energy and the attractive energy as negative energy. But in terms of energy, if you think for quantity wise, energy is still going to be scalar. This axis represents
মানে ইন্টারমলিকুলার ফোর্সের রেফারেন্সে বলছে স্যার?
Sir,
Yes.
the graph on the left.
Abhias, এক minute. Shubro, did you get the answer? Abhias, hold a second.
Yes sir, I got it.
আচ্ছা ঠিক আছে, okay. Shubro is over. হ্যাঁ, Abhias বলো.
I was just saying that the graph on the left is better for this explanation. Like the underneath that one, here's this.
Oh yeah, oh, looks good. Oh, I didn't see that. Yeah, but this graph should what happens beyond this point? Okay, so over here, so this is the point where the equilibrium attractions and repulsions are balanced. So without repulsion, we're gonna have this one. So if they're only attracting, I don't actually know the entire content of this graph, so I cannot essentially tell you every single part about this one. The only reason I brought up this graph is to give you a simple idea that how does that work done actually happen. I hope I don't regret this, but I really don't know all the features of this graph. So please, you can ask me, but I'm gonna tell you I don't know.
Sir, this graph pretty much represents subatomic physics by the whole. So I guess it's pretty important.
It is important. I'm not denying its importance. I'm just saying about the limitation of my understanding. I'm not saying it's not important. No. Every small pieces make up the whole concept. So yeah, I'll move on. So then, acha Raya hat utaisila. Sorry, I forgot about that. Raya bolo.
Sir, in the graph that you showed in the browser, can you go back to that? Sir, এখানে যে মানে আমাদের মিনিমাম পয়েন্টটা যে টার্নিং পয়েন্টটা হয়েছে গ্রাফে,
Yes.
can we consider that as the elastic limit? মানে যে কোনো একটা ম্যাটেরিয়ালের জন্য, বিকজ বিয়ন্ড দ্যাট যখনই আমরা কোনো ফোর্স এক্সার্ট করছি তখনই তো মানে পার্মানেন্ট ডিফর্মেশনে চলে যাচ্ছে, because as you said the atoms become more comfortable at that condition.
Okay.
Can we think about it that way?
I'm not. I couldn't capture this. One more time, please.
Sure, I said that the minimum point, the turning point that we can see,
Yes.
can we say that that it is the elastic limit of the material?
That I'm not absolutely sure about, because what I do understand just from this graph, I mean, I'm using this graph because the bottom is much more visible. Bottom, my bad. So the lowest point is much more visible. So what I'm trying to mean over here is that within this part we're gonna see elastic point. As far as my understanding goes, so far I can remember, this is supposed to be the elastic. This is supposed to be the UTS point.
Acha.
So elastic limit should be somewhere within, and then we're gonna have the inelastic or plastic deformation before the UTS point within somewhere over here, as far as I remember. And beyond this point, you're gonna have the graph that exists after the.
Yes.
That's what I remember so far, but I might as well be wrong. I have to really revise this graph. I haven't done this in a while.
Sir, I had a question, sir.
Bolo.
স্যার আমি যখন আপনি যে বলে আপনি ইকুইলিব্রিয়াম পয়েন্ট থেকে যখন আমরা নিচে আসছি, ঠিক আছে,
Yes.
তো স্যার আমরা জিনিসটা কি লাইক স্কোয়াশ করতেছি নাকি লাইক ইয়া করতেছি স্যার, এক্সপ্যান্ড করতেছি?
Separation বাড়তেছে. If you are moving it to the
সেপারেশন
right,
বাড়তেছে না?
হ্যাঁ,
হ্যাঁ, মানে পোটেনশিয়াল এনার্জিটা তো স্যার মানে বাড়তেছে নাকি?
হ্যাঁ, amount wise
হ্যাঁ।
বাড়তেছে, but that is now happening due to attractive forces. That's
মানে
why,
অ্যাট্রাকটিভ মানে আপনি যে প্ল্যানেট দিয়ে শিখাইছিলেন ওইটাই তো, তাই না?
হ্যাঁ, similar stuff.
সিমিলার স্টাফ। আচ্ছা ঠিক আছে, থ্যাংক ইউ।
স্যার,
হ্যাঁ, বলো।
স্যার ওই যে আরেকটা গ্রাফ যে আবিয়া সাজেস্ট করেছিল, স্যার ওখানে তো ইকুইলিব্রিয়াম পয়েন্টটা মিনিমাম পয়েন্টটা দেখানো,
Yes.
and when you the other graph you were showing, you said that the x-intercept was the equilibrium point.
This is because have a look at the two labeling. Without repulsion, we'll have the black line. With repulsion, you're gonna have the red line. But if you sum this up to, you're gonna get a combined line which is somewhat like this. Here the two lines are exclusively for two individual forces.
আচ্ছা বুঝেছি স্যার, থ্যাংক ইউ।
So if we go for the next part of the discussion, which is the gas laws, basically here from this point we have the new part of your I mean, you have the more elaborate mathematical part of your A2 syllabus. So you have the Boyle's law, P proportional to 1 by V, where T is a constant, or we have Charles's law, which is V proportional to T, where P is constant, or we have pressure law, P proportional to T, which is where V is constant. So you can remember these three laws individually, but we don't usually go for this. Combining, we get PV by T is a constant, which means, and এটার পরে এখানে একটা লজিক আছে, এই লজিকটা খুব ইম্পর্টেন্ট। Students in many cases forget to write this logic and lose mark for this. For a fixed mass of gas, or for a fixed mole of gas, the ratio of pressure, volume, and thermodynamic temperature, you have to mention that, not only temperature, because temperature দুইটা unit আছে, one is the degree Celsius unit and one is the Kelvin unit. So you have to mention this, which unit are we talking about. So for a fixed, কি বললাম, for a fixed amount of gas, or for fixed mass or fixed mole number of gas, the ratio of pressure, volume, and thermodynamic temperature is a constant, and this is called the ideal gas equation. Once again, I have to remind you, whenever we define some physical variable or some physical system to be ideal, it usually means it is imaginary. We use the term ideal to get rid of possible complications of the system. We simplify it, or we largely generalize the situation to use the term ideal gas situation. So if you go forward, it reads that combining we get this. So, and then if we have n mole of gas, this constant is nr. So when R is called the molar gas constant, which is 8.31 joule per mole per Kelvin. Do you use the same constant in your chemistry as well, or do you use 0.0821? Which one do
No,
you?
we use
8.31. 8.31 for I.
Yeah, this is also 8.31.
Yeah. We
Okay.
use
Acha. There are two different practical units that I came to learn when I was in my HSC level. One is joule per mole per Kelvin, which is 8.31 joule per mole per Kelvin, which is a molar gas constant. In some other practical cases, we can also express this thing as the joule can be also expressed as a multiplication of pressure into volume, because you just saw a bit earlier that work done was expressed as P into delta V. So another practical unit for the gas cases exclusively, joule could be also replaced with liter atmosphere. So if you have that unit, you can have a different value. Maybe that has become obsolete now, or that is not considered anymore, because we don't want to have people to mess around with a lot of different units, because that's just mess. We do understand what happens when we see some American videos, miles per hour and whatnot, yards and furlongs. Achha, moving on.
Yeah.
So we have PV by T equals to NR, or we have PV equals to NRT. This is also the two box equations are what we're going to use for our mathematical processes, which works pretty well. Then we have the idea of root mean square speed or root mean square velocity. Now I'm going to talk about this thing a little bit. First, I'm going to talk about why do we need this in the first place. I'll get to the expression in a little bit. The reason we need this idea is for a very practical reason. Try to imagine a certain container of gas, a certain container that is filled up with a lot of gas molecules, and the temperature of this container is kept constant. You do understand the particles are gonna move, and they're gonna move randomly. But if you measure the total displacement covered by all the gas molecules over a duration of time, I'll say this again. Get the parts in your head. If you measure the total displacement made by all the gas molecules over a duration of time, that would be always zero. The reason that it would be always zero, because all these gas molecules are practically trapped within this container. They are inside the container, so they are not leaving out from this container. So they are not practically going anywhere. So resultant displacement of these gas molecules after any duration amount of time would be zero if you consider all the gas molecules. So if resultant displacement is zero, the resultant velocity is supposed to be zero as well, which might give us the wrong idea that because these gas molecules are trapped inside this container, they are not moving at all. But that is not the case. The particles are moving in random directions. They are moving in such a way that they are not essentially going physically anywhere, but inside the container they are moving. To give us an idea that how fast they are moving while entrapped within this container, we bring about this concept of root mean square velocities, where we get rid of the direction factor. We only work with numbers. Let me show you how. Have a look at the sequence of this word. RMS, speed, which is a short form, which I'll be using this acronym a lot once we get past this definition part. RMS stands for root mean squared. So we're gonna have root over, we're gonna have some sort of mean, so addition divided by number of particles, and each of the individual velocities are gonna be squared. So the definition reads like this, or the formula reads like this. If multiple gas molecules have velocities c1, c2, c3 dot 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 n, এখন এরপরে একটা কথা বাদ পড়ে গেছে, which I forgot to make them right, is that at any instant of time, I mean, the gas particles are not going to have a single value of velocity over a duration of time, because they're going to continuously collide into each other. So their velocities are going to change after every collision. So if you want to define that each single gas molecule has one specific velocity, you have to specify that for an instance of time. So instance, do all of you understand the difference between duration and instance?
Yes, sir.
Everyone, please respond. Do you understand the difference between duration and instance?
More or less.
Yes,
Okay.
sir.
Let me ask you this question. How many instances make a small duration?
2.
Many.
an instance, infinitely small amount of time, sir. How do you? What type of question is
Exactly.
I don't
More
think you
than
can
one.
count it.
The answer of this question is infinite number of instances make any amount of time. This is the same question if I ask you, how many real numbers are there between 1 and 2? How many?
Right.
We start from
Infinite.
0.00001.
So how many real numbers are there between 1 and 2?
Infinite real
Infinite numbers, right?
Yeah.
So that's what I mean. Instances is a pretty amazing thing. I might actually give you a link of a YouTube video where they talk about the infinitesimal. There is a very amazing video that I once came across. I'm gonna look it up. It's a good video. I mean, you have to build concept, not calculation, concept. So if we define a certain n number of gas molecules which are entrapped within a container, they all have individual velocities c1, c2, c3, c cn at a certain time instance, where each of these the c1, c2 are velocities, which means they have their individual directions. Then the RMS speed or RMS velocity, we can use both of the term equivocally because they would basically mean the same thing. What we are doing, we're squaring up those vector quantities. Now, whenever you square a vector quantity, squaring a vector quantity essentially mean dot multiplication. Did you guys come across dot and cross multiplications?
Yes.
I mean, is it a part of further or is it a part of regular math?
It is now a part of further maths. এখন পিতে খুব কমই আছে। Further maths আমাদের like vector calculations এর সময় cross product dot product অনেক করা লেগেছে।
আচ্ছা ঠিক আছে। So for those of you who do not know this, just take my word for it. That is, vector quantities can be multiplied in two different methods. I'm going to give you a practical example just to convince you of this fact, but I'm not going to get into the details of this thing. We can multiply two vector quantities to give us an output that is a scalar quantity, or in other cases, we can multiply two vector quantities to give us a vector quantity. One of the very simple example that makes sense to most of the students is that if you think work done, what is the definition of work done? Work done is defined by force multiplied by displacement made in the direction of force. So you are multiplying force, which is a vector quantity, with displacement, which is also a vector quantity. By doing these two products, you are getting a scalar quantity, which is defined as work. In this case, the multiplication that was done, that is a dot multiplication or a scalar multiplication. That's one example. Another example is what we call moment. Moment is defined as it is the product of force multiplied by perpendicular distance of the force from the pivot point. Now get this. This distance that we are saying has to be a vector as well because we are specifying its alignment. You cannot use any random distance from the force to the pivot point to calculate the moment. To calculate the moment of a force, you have to multiply the force with the exact perpendicular distance from the pivot to that force, which means this distance also has a direction dependency, which makes it a vector quantity to be exact. So whenever you are multiplying force and distance between the force and the pivot point, perpendicular distance from the force and the pivot point, you are getting moment. Moment, on the other hand, is a vector quantity. So you are basically multiplying two vector quantities, force and displacement. I mean, vector force and vector distance. And you can from one type of multiplication you can get work done, which is a scalar output, and from another type of calculation you can get moment, which is a vector output. So that's just an example to convince you of the fact that vector quantities multiplication can happen in two different ways. But I'm not getting into the whole jibber jabber of x bx sorry x bx plus ay by plus cx cz. আমি ওগুলো যাচ্ছি না. So what we're doing over here, so take my word for granted, whenever we square a certain vector quantity, that makes the mathematical operation the scalar multiplication. So here inside the root over sign, we are basically squaring up all of those velocity values, and we're getting c1 square plus c2 square plus blah 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 plus cn square. So
স্যার
this
সিটা কি এখানে আসলে কি?
এই যে পড়ো
স্যার স্কয়ার করলে তো এগুলো স্পিড হয়ে যায় স্যার, লাইক ভেলোসিটি আর থাকে না।
That's the whole point that I'm trying to get at, that once you square these velocities, you can obliterate their direction property. They only become numbers.
স্যার আরএমএস বলতে কি বোঝাতে চেয়েছেন? মানে
root mean square.
আচ্ছা, রুট মিন স্কয়ার।
স্যার
বলো।
Sir, in some cases, like the speed of light c is used, but in most cases it's used as v. Why is it c in this case?
That's because the scientists of, I think, wave people and the scientists of the thermodynamics people, when they are formalizing this formula, did not get to know each other in the first place. That's the best explanation that I can come up with, because there are no shortage of letters, but that's how they devised this formula in the first place. I mean, maybe they didn't have a combined conference or something before they came in to develop these ideas, which is a pun. I'm not answering your question, but I don't know an explanation of why they would choose the same letter to dedicatedly use for multiple different variant. But that's how they did it. So we still teach it that way. Because that's how most of the books are written.
Thank you, sir.
I'm sorry, I couldn't answer your question in a satisfactory way, but history, I mean, it's boggling. So so the idea of root mean square velocity is that first we're going to square up all of those velocities, obliterating their direction property. Then we're going to sum these up and divide that by the number of particles, which gives us the mean. So that would mean mean square. And then we would root over, and that would give us an absolute number, which would be the RMS speed, which gives us an idea for exactly what is the average speed of all the particles at a certain instant, which can very well relate to the temperature of that gases of those gas amount logically, which we are gonna see in a bit. So root mean square যদি হয়, then we're gonna write this over here with a root over sign. In applicable cases, sometimes we also use the term mean square. For example, if you're trying to calculate the average kinetic energy of a gas molecule, yeah, I mean, kinetic energy, the formula for kinetic energy is half mv squared. So if you're gonna use the average kinetic energy of a gas molecule, you might as well use half mc squared. So we are simply gonna not do the root over operation. We're simply gonna do the square average. So this is gonna be mean square. The root is gonna be gone. So in other cases, we can also use.
স্যার মানে এখানে অনেকগুলো মাইনর স্পিড থাকার ফলে তো it doesn't matter how much we take, right? Like না, লাইক অনেকগুলা মলিকিউল নিয়ে কাজ করতেছে দেখে আমরা হচ্ছে এরকম সিজ করতেছি, রাইট?
I was about 2 sentences away from finishing this discussion. And then I could very well answer your question. শুভ্রমা কথাটা বুঝছো?
Oh yes sir.
Please. So in cases where we'll need the expression for the RMS velocity in the square form, we might as well not do the root over, and in that case the symbol is going to be like this. So this is the symbol for RMS speed or velocity, where we use this less than greater than sign on the two sides of the C symbol. And if you're using mean square of speed or velocity, then you're just going to not do the root, so you're going to only show the mean of the thing. So C square, which has two less than greater than sign. This is the general symbol for the mean square velocity. I do not know who came up with this symbol, but this is the mathematical symbol we use for that. So mean square velocity or speed would mean only the mathematical average of the squares of the velocities without doing the root over. হ্যাঁ শুভ বলো, তোমার কোশ্চেনটা কি ছিল?
হ্যাঁ স্যার, আমি বলছিলাম যে এটা তো ইনফাইনাইট নাম্বার অফ থাকতে পারে, সো
for a certain amount of gas, for a fixed mass or fixed mole number of gas, you cannot have infinite number of gas because it is calculable by
আমিও এটাই ভাবতেছিলাম স্যার।
Avogadro's constant.
সো আমাদের কি মানে কখনো কি আসবে স্যার এটার উপর কোশ্চেন বেসিক্যালি, তখন কি আমাদের একটা লিমিটেড নাম্বার দিয়ে থাকবে?
Yes. Yes, the answer is yes.
Yeah, বুঝতে পারছি স্যার।
Okay, yes. Then we have this thing, which is the PV equals to 1/3 mc square deduction. Okay, I don't want to go for this deduction for today's class, which I'm gonna do tomorrow, but I'm gonna teach you one last thing, and then we can call it a day, which should be doable within within this remaining 4 minutes or a bit more than 4 minutes, which is the ideal gas assumptions. তোমাদের ideal gas assumption গুলো কেমিস্ট্রিতে কি এস এ পড়ায় না এটুতে পড়ায়?
Yes, sir.
Yes, sir.
Yes, sir.
তোমাদের কার কার কেমিস্ট্রি ছিল না একটু নিচে লেখো বা বলো স্যার আমার কেমিস্ট্রি ছিল না। Anyone?
Sorry, AS ছিল না but O level ছিল।
আচ্ছা, okay. So we found one person, so that brings out the requirement for discussion. The ideal gas assumption is a much more generalized form of the actual complexity that happens within a practical gas. We define this as ideal gas equation because we want to be able this equation to our mathematical process, which is followed by an ideal gas. The ideal gas assumptions, we write them as ideal gas assumption because these things that we're going to discuss over here are not absolutely correct for a practical gas, but this is a scenario something like that you are moving something object and you consider it as negligible and do the math. So ideal gas assumption is something like that. So have a look at these points, and then I have another page added at the end of this thing which also works with the ideal gas assumption, so which is from another year, but I found that table to be pretty lucrative, so I added that as well. Have a look. Ideal gas assumption reads, a gas contains a very large number of particles, atoms or molecules. It is essential so that statistical approximation can be applied. Statistical approximation is pretty important for the ideal gas assumption to be applicable because whenever we use the term RMS, your mean has to physically mean something. If you do the mean of chosen 10 gas molecules out of a population of 10 million of gas particles available in a container, then that would not be statistically feasible. So you need to work with a significantly large number of gas molecules so that you can apply the behavioral mathematics or these explanations to that big group of particles. So ideal if you are considering some amount of gas to behave ideally, you need to have some good number of particles. Now, some good number of particles doesn't necessarily have to be a very large container, because you should understand every mole of one object contains 6.02 into 10 to the power 23 number of molecules or particles of that thing, which means if you consider water has a molecular mass of 18 grams, right? So if in gaseous state you have 18 gram of vapor, that would have 6.02 into 10 to the power 23 number of H2O molecules. So a large number of gaseous molecule is not very difficult to achieve, but it's just a part of the assumption which you have to have. Number 2, particles exert low force on each other except or during collisions among them and with container wall, which means another assumption for the ideal gas is that this is actually a much gross explanation, which I think I was not working pretty well. This table should make better sense. Number 2, দেখো, the forces between the particles are negligible except for during collision, which means one of the particles will collide with each other or they will collide with the container wall, they will be subjected to a force for the duration that collision exists. But for any other part, even when the two particles are passing each other pretty close to each other, not colliding maybe, they are not going to exert any force onto each other, which means all sorts of intermolecular forces or van der Waals forces or gravitational forces or electrostatic attraction forces, they are considered to be non-existent. We're only going to consider that the gas particles exert force onto each other when they physically collide into each other. Apart from that, they do not experience any force. So the only force they experience is the collision forces among themselves and also from the container wall. Number 3, the volume of the particles is negligible compared to the volume occupied by the gas. Now, this is a pretty important thing for you to understand. Volume occupied by a gas basically means the internal volume of the container where the gas is located. Volume occupied by a gas means the internal volume of the container where that gas is located. Do I make sense? So if you keep a certain number of gas within a large container, all the gas molecules are going to cover the whole area. If you keep the same gas even in a much smaller container, they're going to cover that much area. So no matter what is the internal volume of your gas container, the entire gas is going to be contained within that entire volume. This statement or this assumption for the ideal gas tells us that the volume of the particles is negligible compared to the volume occupied by the gas, which means that, I mean, if I give you a practical example to make to visualize it, let's say you have let's say 2 million vapor molecules within a container at a temperature higher than 100 degrees Celsius. So you have a container that is filled up with 2 million H2O in gas state. So if you start cooling up that container, slowly but surely the gas molecules are gonna lose their energy, and beyond 100 degrees Celsius, below 100 degrees Celsius, they're gonna convert into liquid. Whenever they're converted into liquid, all of those water molecules are basically touching each other. So that volume that you can measure in the liquid state is the exact volume, nearly approximately their exact volume, because we have to talk about consider their intermolecular gap as well. But approximately in the liquid state, that volume is the condensed form gap, a condensed form volume of those water molecules exclusively. So we can say that if you divide that water volume by 2 million, you find out the exclusive volume of one of the gas molecules, one of the water molecules. This assumption says that the total volume of the gas is very large compared to the total volume of the molecules only, or they are negligible, or which means that, which in other words, which could also mean that if you have a 1 meter cube container where you are keeping some amount of gas, all of this 1 meter cube space would be available for all of the gas molecules to move around. They themselves would not occupy any volume. আমি যখন গ্যাস লস করে আসছি, আমাদের সময় এই জিনিসটা ছিল যে volume of that each of the gas molecule should be considered as a particle where they have some mass but they don't have any volume. That's how I came to learn this ideal gas assumption. Currently around the globe they have changed this thing a little bit. They are stating that it is negligible, which doesn't very much change the mathematical aspect but changes a little bit of closeness. It brings us a bit more close to the practical scenario. Number 4, most of the time a particle moves in a straight line at constant velocity. The time of collision with another particle or container wall is negligible compared to the time between two collisions, which means the particle's collision duration is negligibly small compared to the duration any particle take in between collision. So মনে করো একটা কলিশন থেকে আরেকটা কলিশন হওয়ার মাঝখানের অ্যাভারেজ টাইম গ্যাপ যদি 1 সেকেন্ড হয়, তাহলে কলিশনের ডিউরেশনটা হবে 1 সেকেন্ডের তুলনায় নেগলিজিবলি স্মল। ফর অ্যান আইডিয়াল কেস ইট ইজ সাপোজ টু বি কনসিডার্ড টু বি 0, এন্ড আমি যদি কলিশনের ডিউরেশন 0 বলে দেই, তাহলে আবার আমাকে হিসাব করতে হবে যে তাহলে তো ফোর্স ইনফাইনাইট হয়ে যায়। That's why they have got rid of the idea of 0 time duration. They have used the term that duration of collision is negligible compared to the duration the particles take to cover the distance in between. And then the last one, the collision of the particles with each other and the container wall are perfectly elastic, so no K is lost. This is also very important because one of the things that is gonna be a part of our discussion in the next class, which actually brings about from this idea. Try to understand this thing. The way we are defining the ideal gas is that the ideal gas particles do not have any force of attraction or repulsion among the gas molecules except for when they are colliding. Which means for an ideal gas, irrespective of the volume, there is no question of potential energy, because the whole idea of potential energy came from the concept of intermolecular attraction forces or repulsive forces for all I care. But ideal gas molecules don't have any intermolecular forces. They only have contact forces, which means the entire internal energy content of an ideal gas will be exclusively coming from the kinetic energy of the particles or gas molecules. The gas amount would not have any potential energy stored as long as we define that gas as an ideal gas. Ideal gas will only have kinetic energy in the form of the motion of these gas molecules. No potential energy would be involved. This is an important aspect which will be very important for our lecture in the next class for the mathematical formulation. So that's the part that they're saying. The collision of the particles with each other and the container wall are perfectly elastic, so no K is lost. K cannot be lost. That is the gas. There is not. Total energy of the gas is the total K of all the particles, which means potential energy of any ideal gas amount is 0 at any point of consideration. So that's pretty much it for today's class.
Sir, so none of the points are actually possible in practical life, right?
Yes,
None of them.
none of them. That's hence the whole idea of ideal. Thank you very much.
Sir,
অ্যাজিউম কেন করে?
To make the math work out simpler.
Oh, okay.
uh, uh, sir,
হ্যাঁ বলো।
sir, why do we have a van der Waals equation in our syllabus in A2?
You don't.
Uh,
Chemistry
how,
thing.
and how accurate is this equation?
Which one? The ideal gas thing.
The van der Waals equation.
Much more accurate because it accounts for all the.
Well, it is for non-ideal gas, yes, but how accurate as in how close to?
Well,
Pretty close, much closer than that. For extreme cases,
I
it's
can get that I can get that it's close to it's more closer to real life, but I mean in levels of accuracy.
well, in terms of accuracy, I mean the equation that accounts for van der Waals attraction force for particle gases looks like something like that. The P plus a square by something into V minus NB equals to RT. So that's sort of a practical equation for the gas. I think it has. I have it somewhere in here. Do I, or do I not? I might. No, I did not make these kids write this equation. I might have it in my earlier lecture, which is the old one. Just a second. I'm getting to your point here, just a bit. No, I don't see it here either. No. Yeah, exactly. This is the ideal gas equation for real gases. So the idea is that because the particles would have some attraction between them, gravitational force, electricity attraction force, or even van der Waals attraction forces. So the total force that they would exert onto the container would be somewhat more. So the pressure should be somewhat more. So that's why the pressure got a bit of an increase. So P plus A n square by V square, where A is a constant and n square is the number of particles that you have available. In this case, sorry, number na, small n represents the mole number and V is the volume. Somehow these variables actually add up to pressure if we use this expression. And that should be multiplied by V minus NB. In this case, B is the molar volume of the gas. Molar volume means how much volume is occupied by the gas for every mole. So if you have n mole of gas and all of those particles joined together, merged together, if they give you a total amount of volume of NB in the liquid state where the particles are really close to each other, then the actual volume of the container which is available for the particles to move around would be somewhat less compared to that. So that is V minus NB. This is a more close approximation to those equation. So pressure will be slightly bigger and volume will be slightly smaller, which multiplied should give us nRT. This is the equation for the van der Waals equation, but we don't have to entertain this in our physics syllabus. But this one approximates more closely for the real gases because we take into a consideration the physical variable that we decided to not look into in the ideal gas equation. So in a physics syllabus, we do not work with this one. But just because you are asking this one, I'm showing you this one. This one is a more practical equation compared to the ideal gas equation. Ideal gas equation is more easier to work with because there are fewer variables, whereas van der Waals equation is more practical, and essentially it has more variables included, so it deals with more problem. For example, for a motion case, if you want to include the air resistance, your calculations are going to become more complicated, but it's going to simulate the situation more realistically.
Sir, in a practical field, is there any use of ideal gas anymore?
We can use the concept of ideal gases for very extreme cases. Very extreme cases means that if you somehow can make this thing zero, and if you somehow can make this thing zero as well. So making this thing zero essentially mean that I mean what I need you to understand that making this thing zero is practically not never possible, but what we can make is we can make this thing very large, so large that compared to this default pressure, this part would become very small. Let's say 10 to the power minus 5 or 10 to the minus 6%. So in that case, we can pretty much consider that this additional pressure can be got rid of. And you can also make this thing reach up to the ideal gas scenario if you can somehow make this thing smaller. Now, B is a constant, which is a molar volume. We cannot make that smaller. So your N has to be quite small, so that this product is also quite small. So one of the things that you might find in your books, which I did not incorporate in my equation, is that real gases exhibit behavior far closer to the ideal gas situation in cases when we have a very small amount of gas kept at a very high pressure and temperature. The more you can achieve, I mean, if you have a really small amount of gas kept in a container that is at a really high pressure, not high pressure or low pressure, high pressure, that if you can keep it at a very high pressure and the temperature is very high, then that will slowly start to exhibit the behavior like the ideal gas. Or in other words, I can say that your PV by T graph will become more linear. For a practical graph, if you plot your PV by T, let's say we just saw in the equation that the product of PV by T is supposed to be a constant for an ideal gas, this equation that I'm talking about. So if you plot your graph of PV on the y-axis, the product of pressure, volume, and temperature on the other axis, you should get a perfect straight line that passes through the origin for an ideal gas. But for a real gas, that is not the case. For a real gas, this thing tends to take a little bit of upward curve. So if you reduce the number of moles and increase the pressure and increase the temperature at the same time, I'm messing it up. I think it's for low pressure.
প্রেসারটা কম হবে না?
প্রেসারটা কমাইতে হবে। হ্যাঁ, ভুল বলছি। We have to reduce the pressure, increase the temperature. So what we are trying to mean is that we have to have a really large container occupied by very few number of particles, few enough so that NB is too small, but then again not so few that the statistical approach cannot be applied. So there is a sweet spot, because for the ideal gas equation to be applicable, you have to be able to have, you need to have enough number of particles where the statistical approximation can be applied. So you cannot really work with 10, 12 particles. You have to have a certain number of particles where the statistical approach can be applied. I'm not really sure about this limit. I don't have any knowledge about that limit, so I cannot tell you this number. So you need to have few particles occupied in a very large container so that the pressure is quite small, where the temperature has to be really high. In that kind of situation, the real gases start to exhibit more like the ideal gases, or I can say that that line of the PV versus T graph tends to become more and more linear. বুঝতে পারছি?
Yes, sir.
Okay.
Thank you, sir. And sorry, Avias, for snapping at you.
No.
It's fine.